Hello everyone. Today we are going to be studying eigenvalues and eigenvectors. Now there are many applications in linear algebra which are concerned with linear systems, and they are expressed in the form of a matrix A multiplied to a column vector x, and it gives us a scalar multiple of that vector x because lambda is a scalar, x is a vector. Remember, this vector x is a column vector and it has size n by 1. Please don't make the mistake of this x is the same as this x. It's an expression we use to convey that this is the size. N represents the number of rows and 1 represents there's only one column. Now this vector x and this scalar multiple lambda, they have a very special meaning. If lambda is x is non-zero in this equation, then we call this x an eigenvector, and it always corresponds to a scalar lambda. Now this lambda is called the eigenvalue or characteristic value. So the relationship given by this equation, ax equals lambda x, where x is a non-zero vector, has a special meaning. We call them eigenvalues and eigenvectors. So let's look at some of the observations. Now, if you guys remember, we talked about matrix transformations in chapter 1. So this multiplication of a vector by a scalar, a vector multiplied by a matrix, and we look at how this relationship is. So x goes to the, so remember this one, let me just repeat this one. We know that this is the linear system equation. So what are we looking at this matrix transformation as? We're looking at this as, you're looking at this vector x. Remember, this is a vector x here. And when this matrix A acts upon x, okay? So when A acts upon x, we get a new vector B. So what you're now looking at is, we're looking at this matrix multiplication as the action on a vector x, which gives us a new vector B via this matrix equation. And we also learned that every matrix equation is a linear transformation. So here we're looking at this matrix transformation. So let me repeat, it can be, this matrix transformation is an action of the matrix A on a non-zero vector which scales the vector x. You can stretch it or contract it. For example, the stretching would be ax equals 2x. Contracting would be ax equals 0.5x. Now this equation, guys, the one ax equals lambda x we're talking about, has many applications in other fields. It's used in physics, it's used in chemistry, pure applied mathematics, statistics. Now in statistics, guys, we will see them as an example of a steady state vector Q, where A is a stochastic matrix given by this relation AQ equals 1Q. For us, more important is to understand what is the eigenvalues, eigenvectors, and how we can solve them and look at various other concepts related to it. So let's go back to our definition again. So now we're going to give a proper definition of an eigenvalue. We say a scalar lambda is called an eigenvalue of a matrix A of size n if there is a non-trivial solution. Remember, this is a non-trivial solution, x, of the linear system given by ax equals lambda x. When I say a non-trivial solution x, that means I'm talking my eigenvector to be non-zero. So now let's go and play around with this ax equals lambda x. Now, ax equals lambda x, I can write this lambda as a vector, times vector can be lambda times I. I is an identity matrix. Remember this one, guys. I is the identity matrix. Times x. Now, if you remember, let's take a very simple example here. So if I say 2 times 1, 0, 0, 1. it is the same thing as I'm writing it as 2, 0, 0, 2. Okay, so it's 2 times an identity. And if I take it as a vector x multiplied to it, so lambda times I, you see this one over here, guys? And I times x. Okay, let's go further here. I times x. So I'm going to say first this 2 times I2. Remember, I2 is this vector and x. I can write this as, so my x is say x1, x2. Okay, so this is 2, 0, 0, 2, x1, x2. We do our matrix multiplication. What do we get? We get 2x1 and 2x2. Clearly, I can take the 2 out. It's common, right? x1, x2. So 2 times I2x is the same as 2 times x. Do you see that over here? So that's what I'm basically applying over here. It's all simple, very simple matrix calculations. Okay, so now let's focus more on what we have now. So ax equals lambda x can be written as ax equals lambda ix. So if you have a little confusion, go back and look at this little example I have done for you. Now let's get this on everything on the other side. So ax minus lambda ix. Now we are going to apply matrix properties. This is a matrix. This also is a matrix now. Remember? Matrix here. So x is a common vector which we can take out. And what are we left with? Another matrix, A minus lambda. So if we are saying that lambda is an eigenvalue of this matrix equation, I can also say that lambda is an eigenvalue of this matrix equation. There's no difference, provided my x is non-zero. So it's just how I look at the problem. I can write this as a simple linear system of equations, or I can write this as this homogeneous matrix equation. Remember, that's of your section 1.5, homogeneous matrix equation. So that's where we are talking about. So we can say that lambda is an eigenvalue of this matrix A if there is a non-trivial solution of A minus lambda I x equals 0. Oh, sorry, it was 1.7, guys. I made a mistake. So this one is a homogeneous equation, but from section 1.7. Okay. So here's this information we get. From section 1.7, we know the above equation. That is the equation I'm talking about is this. A minus lambda I x equals 0. Okay. So this is 1.7 of our Lay's book, and we talk about that as a homogeneous linear system. Now, if the homogeneous linear system has a non-trivial solution, now go back to the theory we learned there, then what does it say? It says that the columns of this matrix are linearly dependent. So if you have a homogeneous linear system with a non-trivial solution, that means my columns of that matrix are going to be linearly dependent. What does that tell us? That we're going to have free variables. Okay, so that means that we're going to have free variables. Now, what did chapter 3 on determinant says? That if you have a matrix with linear dependent columns, then that determinant of that matrix is 0, which basically applies by IMT that A minus lambda I is not invertible. Okay, IMT is the invertible matrix theorem, guys, keep in mind. Okay, so what's the important part here? That eigenvectors are always non-zero, and this is because of the definition of our eigenvalues and eigenvectors. So the question is, can we have 0 eigenvalues? Yes, we can have 0 eigenvalues. There is a theorem related to it. Let's look at the theorem. So it's a little bit coming from section 5.2, but I just thought that this would be an appropriate place to talk about. Okay, so if 0 is an eigenvalue, if and only if A is non-invertible. Okay, non-invertible means that the determinant is 0 and the matrix is not having an inverse, or non-invertible, if you remember, is called that A is singular, if you remember that, guys. Okay, so let's prove this. We say 0 is an eigenvalue. So we assuming if it's an if and only if statement, that means if this is true, then what comes after if and if is true, or if the coming the statement after the if and if is true, then the previous one is true. So we have to prove both ways. So let's start. We're assuming that 0 is an eigenvalue. So if 0 is an eigenvalue, that means what? Ax equals 0x. Anything multiplied to 0? Always a 0. Now, so when you look at Ax equals 0x, what does that mean? Now, clearly my x is non-zero, guys. So if my x is non-zero, that means by theorem 8 that this one, Ax equal to 0, has a non-trivial solution, right? This is having a non-trivial solution. If it is going to have a non-trivial, I'm giving another way of looking by IMT also. So as Ax equal to 0, now x is non-zero. So I'm going to go by the route of determinants here to show you another approach also from here. So what does that mean? It means that by chapter 2 that Ax equal to 0 has a non-trivial solution. That means my A is 0. X cannot be 0, then this has to be 0. If A is 0, that means what is the determinant, guys? My determinant is 0. Determinant is 0, that means my matrix is not invertible. Also, you can go by the IMT way. So anyways, whichever way you want to go, it's okay. Now let's look at from the other point. I'm saying A is non-invertible. That means Ax equal to 0 has a non-trivial solution. Okay. Now, non-invertibility means this one. So what does that mean? Now let's look at this one. 0 can be written as 0 times x. So when I have Ax equal to 0, okay, so from 2, what do we see? That 0 equals 0 times x equals Ax. Now this is by the definition of eigenvalue, and x being non-zero. Remember, this is assuming A is always going to, x is going to be non-zero. My 0 is an eigenvalue. So what is more important for us in this problem is this, that if I say 0 is an eigenvalue, the moment you see this statement, automatically in your mind it says the eigenvalue for that matrix is non-invertible. Or if I say it's non-invertible, definitely that matrix will have a 0 eigenvalue. So they are very much interrelated. Let's go ahead and do some problems related to what we learned about eigenvalues and eigenvectors. Now, we are given a matrix, a 2 by 2 matrix 3, minus 2, 1, and 0. And we're given two vectors, u, minus 1 and 1, and v, 2 and 1. The question is, are these the eigenvectors of A? Now, if they're eigenvectors according to the definition, if, that means A times x, if x is an eigenvector, it should be lambda times x. That means when I multiply the matrix A with that vector, it should actually scale that vector. So that means if I'm multiplying A with u, in my answer, like A times u, when we do it, we get minus 5, minus 1. I do not see any scaling of the vector u. So clearly u is not an eigenvector. Now let's go ahead and do A times v. Now just simple matrix multiplication, guys. So we have A and we have v. When we multiply, we get 4 over and 2. Clearly 2 can be taken out. It is common between 4 and 2. Now what is this? 2 and 1 is nothing but, guys, it's the vector v. Here. So clearly I have a vector. When I multiply it with this A, it actually ends up being scaled. As it ends up being scaled, that means it is an eigenvector. And very important, every eigenvector corresponds to an eigenvalue. And that eigenvalue is nothing but that scaling factor we see. So keep in mind, eigenvalues, eigenvectors, guys, they go hand in hand. Now, let's look at from the other angle. That means I would like to know, I give you an eigenvalue and I would like to know whether it is an eigenvalue. Okay, so let's look from that statement. Okay. Now, we want to show that 7 is an eigenvalue. Now, go back to what we just talked about. If it is an eigenvalue, that means ax equals 7x. And then we apply this as a minus 7i x equal to 0 has a non-trivial solution. Now, if this is going to have a non-trivial solution, by IMT, this matrix will have linearly dependent columns. So the only way we can say that this is an eigenvalue if this matrix has linearly dependent columns. So let's go ahead and do a minus 7i. We do the math here. 1, 6, 5, 2 minus 7i, remember, is the identity, and the size always is the same as the size of the matrix to which it is being subtracting with. So when you do the math, this is what we get. Notice clearly these two columns are dependent. Great. As these columns are dependent, automatically by IMT, we say that this is an eigenvalue of A. Now, another thing to keep in mind, because we have learned about eigenvectors. So we will say, can we find eigenvectors as we know this is an eigenvalue? Okay, now let's go back to the same way we started with a minus 7i x. Now, when you look at this one, a minus 7i x equals 0. Just plug it in. Let's look at this matrix. You know what we're basically, guys, doing? We are writing the solution of this homogeneous equation in the parametric vector form. That's what we are going to do. So if I tell you this is an eigenvalue, the eigenvectors, what you basically should keep in mind, we have to write down the vector parametric description of the solution set of this homogeneous equation. That's what we're, guys, doing. We're doing nothing new. Back to our chapter 1 always. So let's go back to this problem again. So I want to find the eigenvectors. That means, let me write this one. I want to write what eigenvectors I can get. In other words, what is x1 and x2. So we first do this matrix, apply the row reduction algorithm. You must be a pro, guys, by now. So we write this, we get 1 minus 0. Now, remember, we have to write this one. So we multiply. Remember, first we do the math. We then multiply by x1 and x2. What do we get? x1 minus x2 equals 0. So remember, we're looking at this vector x. That's the eigenvector. So we are able to find that these elements of the vector are related. That is x1 minus x2. So when you plug in the values, what do we get? x2 times minus 1 and 1. So that means every linear combination of minus 1 and 1 is the eigenvector which corresponds to this eigenvalue. One more thing, guys, I would like to remind over here is something called the Eigen Basis. That's one of the questions you will have here. So when it says find the Eigen Basis, okay, just to remind us, it says find the Eigen Basis for A corresponding to lambda. Here is my lambda is what? 7. It is nothing but just writing down that vector which we have found out, the eigenvector. That's what you basically. So just pick up the 1 here, minus 1 and 1. So the eigenbasis is nothing but you write the vector minus 1 and 1, and this is a set, which basically means all your so basis is basically all possible linear combinations of this vector. That's what it literally means. You are basically just finding vector parametric description of that solution set. And once you find that, these are the various ways you look at it. Just keep in mind, chapter 1, always, guys. Okay? Now, let's do a little bit more examples to get ourselves more comfortable with this topic. Okay. It says, first of all, is lambda equal to 3 an eigenvalue of this 3 by 3 matrix? Okay, what does that mean? You have to show if it is an eigenvalue. What do you have to do? A minus 3i x equal to 0. That means this matrix has linearly dependent columns. That's what you have to just prove. So look at the problem given to you and try to narrow it down to what is basically your the things you have learned with and how you can make connections. So proving an eigenvalue means proving that the corresponding matrix A minus 3i has linearly dependent columns. Just take those little hints to play with. And after that, what do? When we write A minus 3i, back to our row reduction algorithm. And then what you notice, we have two basic variables. And this is the free variable. Clearly, this homogeneous equation has a non-trivial solution. And hence, this is an eigenvalue. Now, once again, we're going to practice finding eigenvectors which correspond to lambda equals 3. Okay, guys, things to keep in mind. That when we're looking at eigenvectors, what you are always going to do is you are finding down the vector parametric description of the solution set of this homogeneous equation A minus 3i x equals 0. So in other words, you're finding this vector x. This is what you're basically trying to find. You're looking for this vector x. What do? Go ahead, write down A minus 3i, put x1, x2, x3. Then you get a linear system of equations. You try to find out what is the relationship between this x1, x2, and x3. You see x2, when you do the math here, is 2 times x3 and x1 is 3 times x3. Just go and plug in. And when you write it down, x3 is the one which is like taken out. So in other words, this vector x is all possible linear combinations of this vector 3, 2, 1, except x3 to be 0, and that's what is important. x3 should not be 0. Otherwise, it won't be an eigenvalue, and it is lambda equals 3. And once again, if the question says what is the eigen basis for this eigenvalue, just pick this vector 3, 2, 1. Pick the vector 3, 2, 1. And what do? You just write it in this nice little curly brackets, okay? Okay. Now let's look at a theorem. A theorem here, it says eigenvalues of the triangular matrix are always the entries of the main diagonal. Okay. So let's look at this matrix. Clearly, this is a lower triangular matrix. Remember, lower triangle means zeros above the main diagonal. Do you see that over here? Now, this is a triangular matrix, and this will make our life so simple because we're looking at eigenvalues. When you're looking at eigenvalues, that means you just look at what are the values on the diagonal. So they automatically become our eigenvalues, 4, 0, minus 3. And remember, when it is an eigenvalue, which is going to be, we just talked about that if my eigenvalue is 0, that means this matrix is not invertible. Okay, let's look at this one. We have a 4 by 4 matrix, and clearly again it is a lower triangular matrix. This is a triangle, that means where are the eigenvalues? It's 5, minus 4, 1, and 1. Now here, you see 1 and 1 being repeated. The proper way of saying it in matrix algebra is we say that lambda equal to 1 has algebraic multiplicity 2. We don't write 1 twice. We say it in this very proper way. Algebraic multiplicity 2. Okay, again this theorem, it says, another theorem, if you have k eigenvectors which correspond to distinct eigenvalues lambda 1 to lambda k of an n cross n matrix A, then when you gather all these vectors together, v1 to vk in a set, that set is always linearly independent. Remember, our job is to apply this theorem, not to worry about how it came about. Okay? Okay, now let's look at powers of a matrix and eigenvalues. Now, first one, if I have an eigenvalue of a matrix A and say it is lambda, then I would like to know what is the eigenvalue of the square of this matrix A? The answer is simple, lambda squared. Let's do a quick proof. So if lambda is an eigenvalue, what does that mean? A times x equals lambda x. Okay, that's what we know. So a square x is what? Now this is our a times ax. Ax is lambda x. Now lambda is a scalar. You can pop the lambda out and you get ax. Ax is again lambda x. So a square x is lambda square x. Here, very important, if lambda is an eigenvector of A, then lambda square is an eigenvalue of A square. But notice there has been no change in the eigenvector. The eigenvector does not change. Okay. One more theorem. And guys, remember, we will be applying theorems. Here, it says if k is a positive, okay, I forgot, this is an integer, guys, okay? If k is a positive integer, lambda is an eigenvalue of a matrix A, and x is the corresponding eigenvector, then lambda to the power k is an eigenvalue of A to the power k, guys. Keep that in mind, it's important. And x is the corresponding eigenvector. So, example, if lambda equals 10 is an eigenvalue of A, then if I would like to find the eigenvalue of A cube, it is nothing but 10 cube. So guys, here is what my recommendations to you are. Go ahead and do these practice problems from the book, Lay, 5th edition of section 5-1, 1 to 4, 9, 11, 12, 14, 17, and 18. Thank you.